All right, so first off, I'd like to thank everyone for coming to our presentation. We are Team 2, the Vibram 3D printed lattice midsole project. I'm Alex, and I'm joined by my partners, Zach and Megan.
Hi, I'm Zach, and I'm from Annapolis, Maryland. Upon graduation, I'll be working with NAVC in their Carter Rock division at Washington, D.C.
Hi, I'm Megan. I'm from Hammond, Indiana, and upon graduation, I'm looking to complete an internship and then seek a full-time job come fall.
Hi, I'm Alex, and I'm from Park City, Utah. Upon graduation, I'm deciding on a job offer in the Boston area.
So our goal of this project was to design and fabricate a 3D printed lattice midsole to be incorporated and tested in a running shoe, focusing on the heel strike running form to improve mechanical shoe performance through emphasis on comfort, stress, weight, and energy rebound, which is how much energy the shoe rebounds. You can think of this like the springiness of the shoe. Our sponsor was Vibram Shoes. Vibram is chiefly known for their market-leading shoe soles and traction grip. They currently partner with companies to make trail running shoes and hiking shoes. The motivation for sponsoring us was to help develop road running shoes and to seek to learn about and utilize 3D printing processes. So why we utilize lattices and 3D printings in our project? Shoe performance traits that we were looking for were lightweight so the shoes decrease energy exertion of the runners, high energy rebound so the shoe increases a springiness factor to improve forward momentum, and finally, high strength in order for the shoe to take stresses caused by running. Now we use 3D printing since the technique has unique customization for specific biomechanics and different styles to bring in customers. It can also produce unique lattice structures to produce distinct properties, and can also allow for rapid prototyping. A lattice is a honeycomb-looking structure shown on the bottom right of the slide. A diamond is the type of lattice this certain structure is and what we use in our project. So some advantage of lattices are that the structures are lightweight due to the less solid material, high strength due to the structures, and low material cost due to that less material. So here's our project story. We researched what shoes are out there that use 3D printing, what materials are used in typical running shoes, 3D printing technologies and materials that can be 3D printed. We made an initial computer model and completed a finite element analysis. We used all of this of what we learned to create our final model. We printed the parts, built our shoes, and finally tested our shoes. Now throughout this presentation, we'll be taking you through this step-by-step journey.
Research is the first step in our design process. When looking at current 3D printed shoe technology, there are a few standouts in the market. Out of these four companies, the Adidas Futurecraft 4D and the New Balance Duraform Flex are the most similar designs to our own, as they incorporate many of the same principles used in the lattices as we applied them in creating our own.
So some current shoe midsole materials that are commonly used are TPU, EVA, and PU. We ended up choosing TPU due to the high rebound of the material, which again is that springiness of the shoe. The similarity to EVA foam, which is what is most commonly used in shoes now, and most importantly, we can 3D print this material.
As industry leaders have further developed technology, the 3D printing market has progressed beyond the original large, fully commercial machines to more affordable desktop-sized printers. The 3D printing processes have also developed beyond the typical layer-by-layer extrusion of FDM or fused deposition modeling. Unlike FDM printing, SLS, selective laser sintering, uses a laser to sinter a vat of powder and typically needs post-processing and expensive technologies. CLIP, continuous liquid interface production, is another method of 3D printing that uses photopolymerization across a resin, curing a liquid with a UV light layer by layer. This process is extremely precise and can produce parts that are flexible, rubbery, and have strong tolerances. While this process has many benefits, the printers are expensive, upwards of $10,000, and have longer print times, which is why we decided to use FDM printing. We are lucky enough to have 3 FDM printers, gather free filaments, and easily rapid prototype in our apartments. For our 3D printing materials, we started using Formlabs Form 3, the Formlabs Form 3 SLA printer with elastic resin due to the previous Capstone team's research, and found there are many limits to manufacturability and shore hardness. Through research, we determined TPUs are printable on FDM printers and reached out to Ninja Tech, our market leader in flexible filaments, for samples of their products. They were gracious to sponsor us with plenty of their NinjaFlex and Cheetah filaments for our project. TPU allows us to achieve a shore hardness that is rigid in structure, but has enough elasticity when a force is applied to return to its original shape while providing proper support necessary in a shoe. Upon testing, we determined that the Ninja Tech NinjaFlex TPU filament had limitations on shore hardness for ours and Vibram's applications. We determined that the Ninja Tech Cheetah 95A filament was best fit for our shore hardness goals and needs for rapid prototyping. Once we determined our material, we had to test it across many different slicer settings because TPUs are unlike typical FDM materials. In order to properly print the Cheetah TPU, some settings such as extruder, temperature, and retraction must be changed. Shown here are pictures of the test prints that we used to find the best way to print lattices. Since we are printing a diamond lattice shape was used to mimic the shapes of overhangs and print angles that are present in a diamond lattice. The image on the right depicts a test matrix we ran, showing the increase of speed from top to bottom of the image and the temperature from right to left. Lower temperatures and faster speeds reduce stringing the most.
The next step in our production timeline is the initial computer-aided design and the lattice generation, as well as creating a full finite element analysis of a modeled heel segment. To properly start our lattice generation on an actual shoe, we first needed to see the areas in a shoe where the forces are highest. We made a CAD model by measuring one of our feet because we did not have access to Vibram's CAD shoe model yet. To do this, we performed a full finite element analysis of a heel cup model that would be in a standard shoe. Finite element analysis involves placing forces on a model and seeing how that model reacts. When studying a shoe, there are two ways to add forces, static and dynamic. A static analysis of the shoe would involve studying the shoe's reaction to standing still in the shoe. As we can see on the left-hand side, the areas in red are areas of high stress on the shoe heel when a person is standing still. Shown in the right is a video of the same heel undergoing dynamic forces. These are forces that change over time and would more closely mimic the forces the heel segment would be under if a person is walking or running. The video illustrates how a generic heel cup in a shoe may deform under the moving forces humans exert. Once the FEA analysis is reviewed, final adjustments are made to the CAD models and the lattice structures. To create the honeycomb-shaped lattices used in our project, a program called Ntopology, also known as NTOP, was used. NTOP is a software used to create lattices and other complex shapes. These pictures are snapshots taken from the NTOP software. The top picture shows the CAD model heel segment before it is converted to the lattice shape shown in the bottom picture. By taking the CAD files given by Vibram, we were able to carve out certain sections of the fully latticed midsole. Specifically, we used NTOP to create a diamond lattice structure throughout the heel part of the midsole shown in the bottom picture. A diamond lattice shape was used because it avoids shear stresses. NTOP further was used to pull out sections of lattice from 3 different areas of the shoe to create our 3 other design iterations. Choosing the scale of our lattices is a crucial part of the process because it can greatly impact how the midsole moves. This is explained in more detail in later slides.
Our next step of our process is printing our lattice pieces and dremeling out the existing Vibram midsoles. Here's an overview of the 2 approaches we took. We will explain more into what each name entails in the next few slides and show our printed parts. We used the Dremel tool to carve out the parts of the EVA Vibram midsole where we wanted to insert our 3D printed lattice parts. Our first method was called the sandwich method. There are extensive print times of printing a full sole lattice with this material and print process, upwards of 2 days. The heel was latticed to focus on the heel strike running form. This yielded similar results by sandwiching our printed lattice piece between Vibram's insole and outsole. As stated previously, these are all diamond lattice shapes with a 2 millimeter branch thickness, which allows for the most fluctuation in lattice density designs. This test method allowed for us to vary the honeycomb densities in the X, Y, and Z directions to compare and testing, as shown in the top right corner. meaning a lower integer value created more diamond shapes in a specific direction, while a higher integer value created a more spacious and therefore less dense lattice structure. Through rapid prototyping and feel of the lattice pieces bending on different axes, we assumed that the 10 by 5 by 10 millimeter lattice would perform best out of our 3 iterations. Our second method is called the slot method. Latticing inner pieces of the midsole leads to material change while keeping the original midsole wall stability. We slotted our printed pieces into each midsole compartment, where we used a Dremel to carve away the area at each desired location. This approach allows for more targeted testing of the foot in the heel, midsole, and toe box areas. All slot pieces have the same unit cell density, the 10 by 5 by 10 millimeter density as determined through our sandwich prototyping.
Before our midsole can be tested, it must first be attached to an upper of a current shoe model. This is done through cobbling the 2 shoe pieces together. The cobbling process started by first using a Dremel tool to carve out all the areas where the lattices are to be placed. Next, the midsoles and their corresponding lattices are brought into the shop where they are paired with the upper portion of an existing shoe. Once the shoes are chosen, the cobbler will bond the 2 pieces together to create a functional shoe. Shown here are 3 design iterations for the sandwich method. The 3 lattice scales used were 10 by 5 by 10, 5 by 10 by 15, and 10 by 10 by 10, shown from left to right. The other 3 design iterations, named the slot method, are also shown here. All 3 of these iterations used a 10 by 5 by 10 scale and were placed at the heel, midfoot, and forefoot, shown here from left to right.
So finally, we were able to test what we made. To test what we made, we utilized a rebound testing mechanism called a Shore resolumeter to test rebound. Images of this mechanism are shown in this slide. This tests the shoe's ability to rebound a certain amount of its energy back. The way this works is you drop a small knob from the top of the mechanism. It slides down the pole, hits the shoe midsole, and then bounces back up. The highest it bounces back up is the rebound value. There's value markings on the mechanism that show these values. For example, if the knob bounces all the way back up to the top when it was dropped, the shoe would have 100% rebound. Our 3D printed lattice shoes perform about the same as the current EVA Vibram shoe we use as a control group, with our 10-10-10 sandwich iteration performing the best, having a 42% rebound, which compared to the 45% rebound of the control shoe, we were very happy with.
We put on the shoes for short-term field testing. Usually this would be a long-term and survey-oriented process, but for the scope of our project, we put them on, ran, jumped, and walked, and compared how they felt to a control shoe. For the slot approach, all ratings were based off flexion, stiffness, and comfort. The midfoot had more cushion than the control shoe and was supportive and the most comfortable. We rated this the highest. The heel slot was the stiffest of the 3 and rated second. The toe slot shoe was supportive, but we could feel the toe compress more when jumping more. This was rated last. For the sandwich approach, the 10 by 5 by 10 lattice density shoe was rated the highest due to its high cushion and flexion and was more firm than the control. The 10 by 10 by 10 was softer and more comfortable than the control shoe and compresses and flexes a lot and rated second because of comfort. Finally, the 5 by 10 by 15 shoe was harder than the control shoe, flexed less, but was rated last because it was less supportive.
Our final results showed that our entry into the 3D printing midsoles was a success. When tested, each iteration had a rebound that was slightly below the values recorded for the control shoe. The 10 by 10 by 10 iteration was the closest to the control with a 42% rebound versus the control's 45% rebound. During the field test, our shoes proved to be comfortable with the 10 by 10 by 10 iteration being the most pleasant underneath the foot when moving around. Along with the strength and lightweight aspects of using lattices, our goals of comfort, energy return, and stress reduction were all met as well. For future designs, a few modifications could have been made to create a higher functioning model. A rim around the heel cup could have added added to increase the adhesion between the upper mesh and lattice surface. Furthermore, we would like to print the entire midsole since the printers used were not big enough and the lattice may have also been modified so that it would be fully perpendicular to the profile of the midsole. Some additional tests may include more lattice scaling variations, as well as possibly being able to partner with a prominent shoe testing company to receive high-quality data.
We would like to thank everyone that helped us make this project a success, with a special thank you to our sponsor, Michael, and Professor Hauser. Thank you.
The floor is open for questions. I think we have a question here. What was the hard, what's that for the current team? How long does it take to produce one midsole using your method?
So the print times of the sandwich 3D printed lattice blocks took anywhere between 15 and 20 hours. And then the slot methods took around 6 to 8. So that combined with the Dremeling approach and the cobbling, the turnaround could probably be around a day or just around a day and a half for the longer ones.
And just a remark, great job, and I really would like to test these shoes.
Yeah, they came out really well. We're very pleased with the overall product that we received.
Yeah, I don't think the team said it, but this project required quite a bit of coordination because they had to print the lattices, but then they had to get them into shoes, and some of those shoes were shipped, or the plan was to ship them from China, and after they hauled them out, they had to carry them down to a cobbler where in Connecticut. And,
yeah, it was a little hour-and-a-half drive to Connecticut.
So this was a logistics test as well as a design test, a design and construction test. So thank you all, fellows, and again thank you to Vibram, which made this challenge available to us and to the team.